Yeah, today we're going to talk about clustering as well as principal component analysis and Gaussian mixture models. You did walk through the lecture, I presume, through the whole one, so you're familiar with what like unsupervised learning is by now. What is clustering? What is K-means? What is Gaussian mixture models and like PCA? The only thing is, before I want to make this practice period rather brief, just because like very few people actually do have electricity in their homes, and this shouldn't take too much time. And before that, I just wanted to very quickly go through just provide you with some links. I'll send this all on Slack on GMMs, namely how they work. And this is basically a very good kind of like notebook plus markdown guide on using like make blobs generator from sklearn, use these like toy data sets and try to cluster them with K-means like this, or to either like do something more complicated like maximize expectation via Gaussian mixture models. This is a different approach, and this link I'm just going to provide you with, and you can have a look if you feel like it. There's a lot of like very interesting and rather helpful information here. Yeah. Also, I used to give a talk on our student mathematics seminar in Kiev Mahila Academy like half a year ago, somewhere, maybe last spring. And basically my talk was about the probabilistic generative models, and GMMs or Gaussian mixture models were one of the things I covered. And once again, I just want to reiterate that this is kind of a key concept, because key concept machine learning, as it basically acts as both like a clustering algorithm as well as a generative model, and it works on the concept, it fuels on the concept of expectation maximization, or EM, and it can like model very interesting dependencies in data, which is important. And for your work, for your home assignments, you'll just need to make sure to be closely familiar with what like is a count of components, okay, what covariance matrix type is used for each component, and how do you initialize those kind of like centers or centroids. This is how like EM works. You'll have this very similar task on as described in this presentation, like right here on the slide. The task being you'll have a MNIST data with like the same amount of images, and you'll need to fit the GMM model, make sure it works, like it has an appropriate fit, so it works, and then you'll be asked to generate some like synthetic data based on what the model has seen already. Yeah, and of course, before performing like GMM fit, you'll need to reduce dimensions in your data, like do a very simply called feature selection via dimensionality reduction, and yeah, we'll talk about that as well. This is basically like very good example how an old model. It is relatively rather old model, which can basically work and generate images nicely, despite being like ever so slightly founded quite some years ago. And yeah, this will be the task. Pretty much these two sources, I can provide you with both the presentation and this markdown file on the GitHub IO. But without further ado, I think we should switch towards your homework. I set the deadlines like for 10th November, I think, but it doesn't quite matter. I know the situation is hard right now. Situation in terms of in the country, war-wise, and in our like home infrastructure with electricity and water is rather dire, sometimes especially. So I want to stress once again, I want you to be advised that whenever you miss a deadline, and there is an objective reason for that, that is not a problem, you either like warn me or just add a comment, or even don't do any of that, just submit whenever you can. Submit the home assignment as soon as you are able to do that. Sometimes even our services are unavailable, like Distadu or uh, or NaUKMA at UA. And when those things happen, that's of course self-explanatory, you can submit. So yeah, no worries about that. Don't really get so overworked and anxious about the deadlines. So once again, you have researcher's diary here and the assignment 5. Let's have a look at the assignment 5. There are 2 notebooks here. The PCA notebook and the clustering notebook. So there are basically 2 tasks. Those are not hard. Those take on average like an hour to complete each if you concentrate well. And yeah, but let's have a look at both of them. First, the PCA notebook. Once again, you're already familiar with what like dimensionality reduction is, what this works for. But I'm just going to quickly reiterate. PCA is one of the techniques to reduce dimensions in your data. Whenever you have too few samples and too many features, it is a very wise idea to actually remove the highly correlated features and just to squeeze down the dimensions of the data set in terms of like your columns, because that may lead to model overfitting, that may lead to model being trained on extra noisy data. That is not what you want. And basically, like right here, we can build a toy data set. So, I don't know, this was a pre-made notebook. I'm not just going to go through everything here. Have this on Distadu if you need. There's a PCA algorithm which is based on some linear algebra matrix shenanigans and like manipulations called, namely, singular vector decomposition. Singular value decomposition. And what this means is just it tries to find the orthogonal basis of each of the substates in your dataset. Then it creates a basis vector which covers as much standard deviation, or like as much variance. I'm going to refer to STD here as a variance as possible. So you get the vector. Let me show. Where was it? So somewhere not here. So you take a vector and you try to get as much information from all the features possible. For instance, you have your dataset has 100 features and you want like 10 or like 5 even. So this algorithm, via like some linear algebra, sophisticated but not really so linear linear algebra matrix operations, it just squeezes these existing features into one new feature called the base vector, which covers as much variance as possible. So basically, you remove all the data, as much data as possible from your like features from your columns, while also creating the newly existing feature, which was not which was not there before, but this feature actually has hopefully just as much information gain, gives you information gain potential as all those combined together that were removed. And yeah, this is what it does basically. So you calculate the mean and you subtract the mean from the x. Then you calculate. You can use NumPy library to calculate the SVD from the centered data sample or set, like from basically your x. You receive that u as and vt, and then transpose vt into them and then take separate the first like in the second dimension, second and first axis, and those are like the components, or component 1, C1, C2, component 1, component 2, and then there's like this matrix initialization with like diagonals being filled in, and then you make sure that there's the dot product of S and VT is basically closed under x-centered. This is basically not worth explaining too much in depth. All these things, but just a setup. It's just how SVD works under the hood, more or less. There's also the SVD is kind of like built in the PCA algorithm and sklearn API, so you can import the PCA from sklearn decomposition, then like create an object PCA with any number of components. This can be like 5 or like 10, but for example's sake, we'll take 2. Then if we fit transform the original data set that we got, it took some time. If you've noticed, it took like a second or 2, so it's actually quite compute heavy. Then we have these like first 5 and last. Yeah, the first 5 of X2D and X2D with SVD. Those are similar, basically. Those are absolutely identical. So basically, the difference is the basis vectors. And I want to actually show you something. I don't think it's possible to be able to see in there, but
I'm sorry.
Yeah.
Are you sharing the screen?
Oh, I'm not. Yeah.
Because I don't see.
Well, you should have. Damn, that was pretty bad. I mean, I am recording, but I forgot to share the screen. Yes, 1 sec. There we go. Okay, so just a quick recap then. Sorry. Whenever that happens, please make sure to ping me. So there's a home assignment 5, a research diary. Don't worry about deadlines. We are looking into assignment 5 right now. But before that, yeah, there's this cool document here on Gaussian mixture models. There's like a notebook here with all the visualization. You have access to all this. If you have time and wish, you can feel free, like basically, to look through this. This has a lot of like good, well-explained material and great examples. It's like a classic notebook on Gaussian mixture models. I'll provide the link later. And there's also maybe this presentation of mine I also mentioned on the Gaussian mixture models. Nothing too fancy here. You already went through the lecture, and you'll need to create something like a potentially synthetic data generator or on NIST, on the image number dataset, 100-digit number dataset. You just need to be aware of three main things: components of Gaussian, how parameters of GMM, the component count K, so number of components, type of the covariance matrix, and how you initialize the model itself. And you can also read through like some notes on expectation maximization. This is how the model is trained. And this is kind of something you'll need to reconstruct yourself in home assignment 6, not 6, but one of these home assignments, as perform PCA or like any dimensionality reduction, preserve variance, and then you fit the GMM with all that data. And once it has an adequate fit, like with some certain amount of components, you can generate synthetic images. So on the left here you can see the original images are original images, and somewhat of a more like crappy ones are on the right, the generated ones. That makes sense, but yeah, enough of that. I've been explaining the no worries, we haven't gone too far about the one of the first assignments. So if we go through assignment 5, you have 2 notebooks here, 05 PCA and 06 clustering. We're on 05 PC right now. Basically, yeah, I'll skip this. This is not that important, but you can of course reiterate this on your own if you want to. But basically, SVD is kind of the underlying principle in PCA. This is what I've been trying to explain while not showing the screen. Downloading the screen, sorry. So this is the PCA kind of from scratch, while this is PCA using sklearn API. So well, this is calculated. This has the same kind of logic here. Just call the object and pass the number of components. Who writes like that? Jesus. There's like x to d, which is a scalar nappy, and just transform, and you have a look at this. While there's also this one is calculated like by hand manually with NumPy max, and these are the same pretty much. However, they differ by size, and they have like different directions in the latent space. So one vector is like pointing to one direction, the other one in the other direction. That's the only difference. So you can inverse transform the data if you want, using PCA, of course. So once again, you can squeeze in the data and create new vectors and remove many other unneeded useless features. But you can, of course, provided that the PCA object PCA kind of like algo is still existing in Python, you can call an inverse transform method and get the the default values for features via this approach. And let me zoom in also slightly like this. So there is some information loss, of course, and this kind of recovery of the original information is not completely exact, but it's just a inverse mapping in the initial space. And so not all of these are like similar. And there's of course a mistake, slightly above 1% mistake in terms of information loss, which is all right, I guess. It's not that terrible. And there's a linear mapping in the default space using SVD, so the handcrafted or manually calculated SVD, the X to D using SVD. This thing is something that was exemplified here, this part, which is like only using NumPy without sklearn API. This is how you can do this, how you can inverse transform the squeezed data back to the original data set. And to get the identical result, you need to center the data as well by subtracting the mean from the original inversed data set. So this is how this happens. And sklearn, it's mentioned sklearn auto handles this. It does this automatically. So then you can also have a look at the main components. So probably two vectors, the vector 1 and vector 2. These vectors describe, let's see how much of the data set. And yeah, of course we can have a look at the handcrafted principal components. So whole new component basically are principal components. These are similar almost, like almost identical. They have different signs once again. Something that was mentioned here, that like these two approaches, they only have a difference in the vector directions. Yeah, so this is the same thing, Let's see the variance, explained variance ratio. So this vector, the first one, explains 84.2% of the data set, which is like insane. You probably like purge a lot of features from this study. I don't quite remember what's here. Yeah, there are quite some number of features, like Argent. Yeah, and basically it squeezes out the information so well that the first vector can explain 84% of the data set. And the second one, or namely this one, can explain the other 14.6, totaling, you just sum these numbers and subtract 1, take an absolute value, and there's this 1.1%, which is incredibly well positioned dimensionality reduction. It does allow us to use only two vectors from like, I don't know, 20 or something there. Maybe less, maybe more. Might be mistaken. I don't want to talk about something irrelevant and the amount of features there, but still, this means that this dataset preserves this loses only 1.1% dispersion, and it preserves namely this much variance or dispersion or standard deviation, 98.8%, which is quite a lot, 98.9. This is the ideal case. You should always, whenever you perform like a dimensionality reduction or PCA in specifics, in your research projects, in your assignments, in your industry projects, wherever, you always are aiming to at least preserve 95% of variance. This is like the key number. It's kind of like a tip from my experience. 94% is just about right. If you have more, that's great, but usually it's very dicey and very dangerous to go below this number. So if you if you did PCA and you got like 88%, you could lose quite a lot of information and get a much poorer model. Yeah, so the singular values, singular number values basically in the variance explained is like maps to this kind of very simple interpretation where you divide where you square the s, the singular values, into just divide over the sum, and they kind of like sum up to 1, like to 100%. And this we do not use because this is the least usable vector. We only use these first two. Yeah, okay, of course, visualize with some weird libraries in Python, which I've never seen, like MPL toolkits. Don't ask me, I don't know what that is. Matplotlib patches, I guess that's fine. So this is basically just two linear spaces of x's, and then you grid them together with a mesh grid. You calculate components, where PCA.components, then you transpose them, and then you calculate z, which is like normalization. And we have some visualization here or not? Oh yeah, there we go. So this is our distribution. Oh yeah. So there was not 20, it was 3 features. Now I'm correct, so now that's fine. So 2 of these features, 2 of these vectors, they kind of absorbed the information from the existing 3 original vectors in the dataset. 2 new ones were created, and those like describe 98.9% of the data. Like something that is illustrated on this figure with a 3-dimensional space, and just it's kind of like, I don't know, 9 p.m. or 12 p.m. like an clock, if you imagine, and just kind of captures a lot of dependencies and makes things work quite well. So yeah, let's move on. This is another visualization in the 2D space with Z2 and Z1. Basically, this is once again what our kind of like semi-loop data set, and these 2 vectors seem to be like describing the data, the transformed and normalized data at its best. Yeah, there are of course many other use cases and examples where you can like stretch the data and rotate it and use some directions with cosines and sines, what's linear algebra, create projections. Yeah, we can have a look through that. Let's see the demonstration. So basically, once again, the 2 principal components, I don't know how much do they describe here. This is a completely different data set, but obviously this is kind of what looks like an adequate principal component analysis and dimensionality reduction, because one of the main basis vector, or like principal component C1, goes along the the imaginary data distribution across its mean, and not like deviating too much left or right, and C2 is kind of orthogonally basically. Hope you have been able to see my screen. Orthogonally just kind of traverses through the latent space and through the coordinate space, and just covers the other part of the information that is also vital, the standard deviation part. And this is just Z1's how much how much of a variance is there with respect to our mean. Yeah, your task will be to work with NIST, I think. We'll just import our usual libraries, PCA, get NIST, get the data. Oh, is it going to load to NIST now? Okay, let it be. So there's an important thing here called selecting the number of components, like a very important and vital concept. It's of course also good, fine and dandy if you like preserve 95% of variance, but it's not always easy and trivial to actually come up with this exact number, correct number of these components. Do not go like 92% or 85% or something like that. Just maximize as much as possible. So this is another task and comes with experience, with your visualization as well. So yeah, I just did some splits. Let's have a look at the image. I'll have a sample. Why do I have a sample? Because we don't need the sample. Yeah. So we got that. How's this? What? Slice none. How do you mean? Anyway, this pretty much don't need that. Let's train a PCA with these parameters. Just call PCA fit x train, or the images, or the matrices, right? And then we calculate the cumulative sum of the explained variance ratio across all the vectors, and we check the maximum value using the cutoff 0.95, and then add an extra 1 on top of that. That gets us the number 154, which is basically, if you're wondering what this means, we have 28 by 28 metrics on our image. It's a grayscale image, 28 squared, 184. 184, or D, or dimensions, or number of required principal components, is basically the most adequate number we have to find out of new vectors we need to generate that can express these 784 pixels with the same kind of variance and information being kept, and also like to reduce the model complexity, make the machine learning models run faster and perhaps even more smooth and consistent. So we're aiming for this number. Very, very elegant and exquisite as far as I'm concerned. And let's see here. And there's a visualization basically of these dimensions and the explained variance of which vector. Sorry. And there's one concept called elbow, which is something where when you like bend your hand and there's this typical position for the elbow, we kind of extrapolate this into some of our like computer science and applied mathematics dimension, and we imagine this this plot where on the x-axis we have the number of dimensions, and on the y-axis we have the explained variance, and we have a trade-off. The bigger the dimension count, the higher the dimension count, the higher the explained variance, of course. But this is a nonlinear function, by any means, of course. This reminds more something like 1 over x or something like that, and hyperbolic to me. But basically, this like very few dimensions literally lose too much information. Like 50 dimensions, let's have a look, only have like 82% of the information or something like that, or maybe even slightly more. There's this elbow, or this kind of bending of the curve of the plot, but you need to kind of look through the whole figure and try to realize what would be the optimal value, or as our kind of like calculations here already suggested to us, the number of somewhere about 154. We have a look at here. So we still get quite a bit of variance here because the slope slope is rather decent here. If we take like the derivative and just see what's the slope here, it's going to be still quite steep. But then once we get to this point, and once we get to dimensions 150 plus, our like f prime of the function would be more flat, and kind of like asymptotic to this the further part of our plot. And somewhere about at 154 we preserve 90 something % of variance. 93, 94, 95, maybe 95, somewhere about 95. Yeah, of course, because it's at 95. This is how you can like kind of intuitively understand the concept of variance preservance in depth, and what you will need to do to actually complete your homework on MNIST. So yeah, just you keep 95% of the components. In a fraction way, you fit transform to x reduced. Like number of components, meaning you can pass the preserved variance here. This is not the number of components, like the number. And there's a number 154. And then we calculate the variance, just the sum a PC explained the variance ratio, and we get 95, slightly above that. Exactly what we need. Excellent. There's a PCA now. Now we call a pure PCA with 154 components. Someone writes very nice code. There's a fit transform and an inverse transform, and we can plot some digits with this function. Let's do that. We can't plot because something went wrong with a object type. Anyway, this is basically how this works. The most important concept to understand is just you need to preserve 95% of the variance, as well as reduce the dimensions as much as possible. To do this, you just need this kind of nice little plot and this piece of code with a cutoff, and this will provide your data set with like provide you with enough information about your data set. How many dimensions can you like quote unquote kill to retain the same amount of information. There's also a variation of PCA called incremental PCA for high dimension datasets. This is a whole separate story. I don't know if this should work. This works maybe a bit faster. So if you transform, then you inverse transform. Maybe this will work now. What's going on? I don't know what's the problem. I don't want to fix this though now with the shapes. So you can of course check both PCAs. They have the PCA incremental and the normal PCA. They have the same means, and there's a problem. Kind of, they have different. Yeah, of course, they should have. This doesn't work right now, but obviously, but they have different compression results, and that's kind of makes sense because they have the under the hood different algorithm, and they compress in a different way. So, do you have any questions on this one, real quick? Okay, no questions. Then let's proceed to quickly go through your test task, the assignment. So you have your MNIST dataset. You're familiar with it right now. You have to just split it into train. This is a very nice formulation. Into train and test. Into train and test, namely 60,000 and 10,000. Then you train random forest classifier and calculate the inference time, the training time. How you do that is just, I always forget. I always forget. Let me see. This should no print will be pretty bad. So there's this thing called wall time. You just can use a magic cell in Jupyter Notebook called percentage sign time, and if you like, this is a bad example, of course, because this runs too fast. If I had printed, it would be different, but still. For models, it shows you wall time, which is like a whole time for the cell. There's also a CPU time, which should be somewhere about that, maybe slightly slower, slightly faster. This is a very cool and fast way to measure time, but of course you can always use something like import datetime, no, it's from datetime, import datetime, and then just use something like now equals datetime now, and then like once you run the cell, for instance, let's do this here. Like once you run the cell, we just print datetime. We need to, of course, reformat. This might be messed up because I don't quite remember whether this will work, but this will. There's this difference in time. So this is how you measure how you evaluate the training time. And then the second part, you just need to use the PCA and maintain 95% of variance. Pretty basic what we covered right now. Retrain again with this data, like with the much less of a count of features, and then you compare the time and the performance of the model as well. Last but not least, you have to do the same thing for logistic regression. Kind of easy, just copy paste code, you replace random forest with log reg, and that's it. Just write a brief summary of what you've been observing. This is the first part of your assignment. Yeah, this is kind of if this is too overwhelming, I mean we have a second one as well. If this is too overwhelming, it's okay if you do this one on this week. Not a problem. But just I'm not sure. I don't think clustering is too complicated and sophisticated. So I'm just going to explain the notebook and some key concepts right now. And I would encourage you to complete the tasks as soon as you see them fit for you. It's not like an obligation to do those before 10th of November, both of these, but that's like a strong advice and suggestion, I guess, not an obligation. Yeah, so there's also a second notebook. We're looking into 0.6 clustering now on the distado. So what's here? So classification versus clustering. We'll load some more of our favorite iris dataset with flowers. We have 3 flowers now: Setosa, Versicolor, Virginica. Plot them. Then we suddenly remove the labels. Here we have labels. Here we have nothing. What do we do here? This is a good question. Suppose we have a dataset without any labels. So in the second case, once again, this is a clusterization task or unsupervised learning. In the first case here in the left, in the first figure, this is a supervised learning classification because we have labels. So we use Gaussian mixture model. The same good old sklearn API, sklearn.mixture, import Gaussian mixture. Then we, this is kind of a bad style, don't do this ever. Just initialize the model first. GMM like this, and then you use GMM like right here to fit. Okay, this is all right more or less, but before that was a bit weird. So fit on our X data on the iris and predict on X. Then we apply mapping by assigning cluster IDs for each predicted cluster ID, and we see what's going on here. Well, we have three pretty decent clusters: a blue one, and a green one, and a yellow one. If we compare to what we saw here, I mean the colors are different, but that doesn't matter. They clustered the information quite well, I guess. The GMM, I mean. And let's see the number of. Yeah, this is the inverse accuracy. Yeah, because obviously there are 157 samples and they classified correctly 153, and the accuracy is supposed to be 0.96.6, but as the labels are inversed, it shows the inverse accuracy. That's fine though, not to our worry. And also KMeans, just a very classic and robust and traditional clustering algorithm. Make a very quick showcase data set here with blobs, 2000 samples. We have blob centers here as well. So 1, 2, 3, 4, 5 blob centers, basically kind of like pseudo clusters. And we pass these blob centers into make blobs data set and some standard deviation right here. Make a random state, and let's see what we have. So we have these clusters, 1, 2. I hope you can see them. 1, 2, 3 on the -3 x-axis. Then we have this highly dispersed cluster, and then there's another one, even more dispersed cluster in the right part of the figure. So let's train KMeans to kind of attempt to classify these. Just import from a sklearn cluster KMeans, like you did in the SVM task, I think, in computer vision. there's this thing as well. The clusters, you presumably put 5 because we kind of like we suppose our data has 5 clusters from this figure, and you just call a fit predict. So here it's written properly, like they defined k-means and then they call fit predict without like using this very weird structure here. What was it? This is very weird. I never did it. I'm just kind of like distracting myself, but that's fine. That's kind of an important observation. So we just predicted some of the centers for each element, and we get the yprad. And then we have labels for cluster IDs, and yeah, that's just some checks. Let's see the centroids. I'm just curious. Let me copy this and have a look here. So what is this? What do we have here? Mine is 2.8, 1.8. So the first one, this one is this one. Then 0.2, 2.25. There's probably this one. Minus 2.8, 2.8. This is this one. And get out. There's also minus 1.5, 2.8 is this one approximately, and minus 2.8, 1.3 this one. So basically, as you can see, it very much did a great job of approximating those centers. And yeah, even though there's like different dispersion and different variance and different positioning in terms of Cartesian coordinates, still the model managed to converge and provide us with good, decent cluster centers. Yeah, we can of course evaluate existing clusters by trying to calculate the centroid distance and just some predictions, but there's of course some decision boundaries involved with Voronov diagram. Yeah, this will take too much time, but let's just have a look here. There's decision boundary that just defines the potential use cases for each of these. Not use cases, use boundaries for each of these clusters centroids. So obviously these do not belong. Like if you have a look here, never mind. You have a look here, like these pink spots, they do not belong. Clearly, do not belong to this cluster. And well, this one is not also this green one. Does not belong here. This is not 100% consistent and exact, but it's a good approximation, which is more than enough for us. There's of course, yeah, moving on, hard and soft clustering. So instead of like strictly assigning and evaluating distance-wise each point to the centroid, we can do something like not assign the cluster to the element, but kind of like try the distance approach. We can use transform for the original dataset using KMeans and try to perform the soft clustering here. And then we just calculate the distance to centroids. And this is kind of like a different approach. You can read in depth what's the difference between hard and soft clustering. I'm not going to go into much detail here. Then, of course, a very important concept of initialization. In KMeans, like judging from how you initialize your centroids, your algorithm can converge faster or slower, or cannot converge at all. And this is kind of very important. So there are different algorithms. You can look through the documentation. Cluster centers. I think there was mini batch KMeans. There should have been something here on that. Oh, see, methods for initialization. Let me demonstrate now. Come on. Okay, so methods for initialization. So there's a KMean++, which selects initial clusters for KMean clustering in a smart way to speed up convergence. You can have a look at what that means. This is probably the best choice. There's a random one, which is kind of like KMeans++, but still it just randomly samples across the data and converges rather well. And there's pretty much it for this algorithm specific one. Usually people, by default, the value of KMeans++ is used. So you can have a look at that. So cluster comparison, there's a solution 1 and solution 2 with a different random initialization. Well, if you ask me, I don't know what's going on here. What? Which cluster did I miss? 1, 2, 3. 1, 2, 3. So see, this failed. They both failed at this corner, lower left corner, which is kind of funny. Is this reproducible? Interesting. So still, it's kind of like a very poor clustering here, but you can see that the decision boundaries only remain the same in the left-hand side corner of the figure. So the yellow and the gray zones are the same. The other ones kind of like messed up. In one and the second picture. Yeah, there's a concept of inertia. Yeah, there's such metric even. Same like in distance space, it's a metric, inertia, and just it sums the distances from the elements to the centroids of respective clusters and evaluates that. So there's some inertia 211, and if we calculate this by ourselves, we calculate the distances, we just transform x with k-means, then we sum the arranged like the number of samples in the x-dist, and we check the labels, we square it up as kind of like this is a to d, and the distance is going to be the same. And there's also a score method that for some reason returns a negative inertia, kind of also a quick way to access this number. Yeah, there's an optimal number of clusters. So if we try something more tricky here, we try instead of 5, as they're like in factuality there are 5 clusters, we try 3 or 8. So 3 clusters, it's very crappy. It kind of like doesn't describe anything here at all. There's like 2 here, 1 here, and 2 here. With 8, it's also tricky, but it's kind of maybe not less. Maybe slightly better, because like these are correct, these 3 are correct. This one is split in 2, this one is split in 3, the right one on the 8. And we can also calculate inertia. So on 3 clusters, the inertia is 653, which is a lot. And K8, with 8 centroids, the inertia is 119, which is much better. The less the inertia, the better. So the inertia will decrease with number of clusters. And of course, like we can set like k equals 1000. Inertia is going to be very small, but this of course means that this metric cannot explain to define like optimal cluster count. So instead we can use the dependency graph where like the inertia is plotted against the cluster count. So let's do that. So yeah, this is a very important thing. This is even the better elbow. So the inertia, of course, is the distance to, or the mean distance of all the samples to the centroids, and if you plot it against the number of clusters, or like, it looks very similar to components and PCA. There is this elbow point. Once again, if the slope here is has the sharpest edge, even though the edge is still this edge exists, this is probably the optimal number of clusters or the centroids. So 4 in our case, and so if you select something further than that, the inertia, of course, is going to be lowering down, but the complexity and the overfitting potential of the algorithm is going to be increasing. If you select something below number 4, the inertia is going to be too big, of course, like underfitting. So the elbow is number 4, meaning this, yeah, self-explanatory. So we can like suppose that 4 is a good number for a cluster. And let's see the decision boundaries. There's 1, 2, 3, 4. I mean, that's fine, I guess. That's pretty much fine. Oh, solid score and solid coefficient. Yeah, this is also kind of a separate topic and an important one. So basically, it is defined as like a coefficient or a score in some of the data sets. And the coefficient is basically expressed by the formula of B subtract A over maximum of A and B, where A is something like a mean of distance between the element and the other element from the same centroid cluster, and B is like a distance from the same element to the examples or samples from this like a neighboring cluster. And this function, this kind of like metric, has a distance range of from -1 to 1. And yeah, let's have a look at this one real quick. This metric exists in sklearn metrics. Calculate the label. We've just passed the X dataset itself and the labels of KMeans. And we get a 65%. The silhouette score. And then we check each model for a silhouette score. Then we display it. So the best silhouette score, of course, we can see is at 4. Something like almost 70. With 5 at 65, as we have seen. With 3 and 2, it's lower than that, much lower. With 6 and 7, it starts to do some weird tricks, like up and down, but at 8, it suddenly falls very low. This is another evaluation metric, so you can either choose 5 or 4 here, obviously from this diagram. Some more examples. With K3, with K4, 4 is like seems to be most robust. K5 is fine. 6 is already pretty bad. Yeah, there's clusters of an incorrect form, or blobs, like these very interesting things, like the stretched out non-normalized distributions. And suppose we have these kind of one cluster here, one cluster here, and this big one, this first one. How do we deal with that? Well, obviously we can try something like certain initialization points, just number of clusters 3, or with an init technique and init and without it. Let's see what happens. So the inertia is better on the right, I think, even though it's like KMeans bad. But yeah, of course, the inertia is not like a susceptible good enough of a metric. So in the left figure, you can clearly see that this is absolutely correctly clustered, as this stretched out distribution and the one below it, the pink and the green ones, are kind of correctly classified. And of course, the gray one remains for the 3 cluster centers, while the one on the right, with no proper initialization, seems to struggle. It just slices these two in the half, making them completely unviable, and only correctly predicts the green one, the big dispersed one. What is this? Clustering for image segmentation. Okay, let's see. I'm just curious. We downloaded some image. Hands on a mouth, some sparkling ladybug. Oh, we're going to have a look at ladybug. So I just trying clustering on 8 clusters, KMeans, on some image, and finally, thank God, it finished the processing. So ladybug, we segment clusters here, use some colors. Nothing too fast, just an example of that you can use KMeans, even computer vision, for some certain applications. While it processes, I'll just quickly iterate over Gaussian mixtures. Well, it's just a very cool model that's based on the normal distribution. It involves using some certain number of samples, assigning this count of centroids, and also has different strategies. Yeah, let's just have a look. Original image. Oh, yeah, it's pretty cool. So the original image has a ladybug on the flower. Then there are like 10 colors retained, 8 colors retained, 6 colors retained, 4 and 2, and the image is dying out. Pretty cool, I guess. I don't know what's that for here, but let it be. So back to Gaussian mixtures. So we just generate some random blobs, 2 sets x1 and x2. We import the Gaussian mixture, import the components. Just import the just create the object itself of the model, pass the components to number 3, init by 10 steps, and just fit the model. Let's see the weights. The model has different parameters, output, as once it's the fitting and training is complete. There are weights of the model. There are means of each of the components, and there are covariances of each of the components. Covariance is an important concept which has to do a lot with variance and correlation. You'll need to like familiarize yourself a little bit more with this later. So let's see if the algorithm has actually converged. This is a very cool thing. Very few models and like very few APIs show if the model has converged, but the Gaussian mixture just shows that it's true. The model is fine. How many iterations were there? 4. Good. Before there was like 13 or something. There's also this mix correlation, like association of elements with a mix, which can be considered as clusters, which predict probability, like in scoring tasks, and then we can synthesize new elements according to the distribution we received. So we define new image and new label object and sample 6 of them and just see what's going on here, and new labels, and there's also a probability density function logarithm that can be retrieved via score samples like this, for your own satisfaction, I guess. So we can display the decision boundaries and the limits of probability density function. I don't think this will work, but maybe we'll see. Maybe it works. Oh, it does work. Wow, look at that. Okay. That looks a bit... yeah, pretty reasonable, but still overlaps. There's this certain separate cluster which was a very sparse and high variance one. And these are these two that are very well modeled by Gaussian mixtures. This is from the example we had here. I'm just reminding you this one. So this looks quite legit, I guess. And we, of course, can change the type of matrices. matrices covariances. This is something I mentioned here on the presentation. So you need to make sure you pay attention to component count, covariance matrix type, and initialization strategy. This is all displayed in our, like, why this is important. It was displayed in these like notebooks. You can change covariance type from full to tight to spherical to diagonal. I'm not going to go into details right now because we don't have much time. I'm even like over. I didn't expect this to be such a actually big amount of information, but both for me, for you, like time-wise, but still, we gotta do what we gotta do. So let's fit all these four models. Done. Let's compare Gaussian mixtures with this nice little function. Let's just plot Gaussian mixture each and any one of those. So covariance type tied. This is kind of like separately tries to equiprobably and equidistantly assign the centroids to these clusters, even though they're kind of like obviously can be skewed and separated in another way. Spherical. Spherical makes a mistake, I think, because it's the same thing basically. It does what it did here. It just slices these two on the left in half, and that doesn't work because that's not correct and kind of like an inaccuracy mistake. Then we see a full type. Full seems like something we had here by default, yes. And there's also the diagonal one. Oof. Well, it's better than spherical approach, I suppose, but still quite far away from the truth. And there's also GMMs are so versatile. They can generate data, they can cluster data, but they can also detect anomalies. Basically, any kind of like elements in the that surpass the threshold, certain threshold, they are considered like anomalies or outliers, if you may. So you just score samples of X with a Gaussian mixture to receive densities. Then you get you just apply percentile, just the usual numpy percentile to the densities and receive a threshold. If you want like 4% to be gone, for instance, and then you like just the threshold, just threshold the X based on the densities and the threshold. Let's see what happens here. So these are considered outliers. So that's a very nice illustration how basically those are outliers. I mean, I suppose these ones are debatable, like these close ones, but maybe still they're kind of like mess things up quite a bit. This is obviously quite good demonstration on this cluster right here, and this and this. And yeah, not bad, not bad. So see, it basically finds anomalies for you. You don't need to calculate any standard deviations beyond 3 sigmas or something, or 4 sigmas. God forbid. Very good instrument, very undervalued, and very kind of like very rarely heard of as of right now, unfortunately. So for your task, for your homework, you need to download NIST. You have it already. You just need to split it into train, test, validation test, as we did, you did it already many times. You need to use PCA to reduce dimensions. Then you need to cluster your data set using KMeans, and kind of like simulate the unsupervised learning. Try to find the optimal number of clusters using this elbow technique, or like this technique, or elbow technique, or anything you like. Maybe you can come up with something else. Then you train a Gaussian mixture model, and you once that's done, you just synthesize the new elements using the GMM and just visualize them. For demonstration's sake, this is what it looks like. Of course, I'm not able to show my own assignment completion from the year ago, so this is just data loading. Then you scale data, of course, because those are non-scaled. Then you apply PCA, you set up the variance. This should be more than that, but actually this is fine. Maybe this is fine. Maybe 154 should be better, but I did this because I wanted faster to compute. Then you have this elbow thing, and you select number of clusters. You train the GMM, different parameters if you want. Oh my god, did I write this? And then you have a look at the means, you synthesize new data, just GMM sample, and well, it counts, see the distribution of classes that you synthesized, and inverse transform, and then generate images. You have an image, you take it, reshape it, then round it, and do a binary mask, and there we go. This is something that was created basically synthetically, superficially. Well, yeah, that was that. Any questions as for either principal component analysis or clustering from your side, or any other questions?
Still no question.
Okay. Good. Yeah. Then I shall thank you for attending. I know it's not that convenient right now, but this had to be done. This is quite an extensive material, and needs to be covered. Feel free to ask me any questions on Telegram or on Slack if you want. If you're facing some difficulties, and don't ever get anxious about deadlines. Those are not a problem. In this case, I shall once again thank you and wish you a pleasant rest of the week. Stay safe, please. Bye. Bye, everyone.
Bye.